Yeah, you can start now.
Yeah. Can you see the screen?
Yes, yes, yes.
Okay. So in the last class, we had seen this problem of angular momentum. So this problem is something like we have the angular momentum states denoted with this symbol L comma M. Now L can be 0, 1 or 0, 1 by 2 according to what we have observed, 1 by 2, 1, 3 by 2, etc. And given L, M will vary from minus L to plus L. So for getting this, we started with commutation relations. Okay, so we start with this L comma K. But angular momentum, that is L upper, is defined as R cross T.
So what happened? The screen has gone.
Yes, sir. Yes.
Hello.
Sir, Sir is left out.
Oh, okay, okay. Maybe I'll call him, whether he knows that. Yes. For Sathyanarayana, now screen is not seen. You.
Yeah. So was there some? It has got disconnected, right?
Yeah, you got disconnected.
Yeah. So the internet signal is very poor today. I don't know why.
Okay.
I have to share again. Is it visible now?
Yes, yes.
So we could have done this problem by using. We know that your x your operating on any function is simply x multiplied by x, and px operating on any function is h bar by I into df by dx. So if I use these things, then I could have got some differential equation for this L square and LZ. Okay, differential operators. So differential operators. Out, write the coordinate. So in terms of what is called r theta, spherical polar coordinates, you could write this LZ as h bar by I into partial derivative with respect to phi. So this is the operator. And the L square operator is minus h bar square into 1 by sine theta, dou by dou theta, sine theta into dou by dou theta, plus 1 by sine square into dou square by dou phi square. So if you ask a question, common eigenfunctions of L square and LZ. I'm calling it LZ here, but this is same as L3 that we called earlier. So they are basically spherical harmonics. That is YLM theta phi. Okay, one can solve this differential equation by separation of variables. Then you will get this. Such that square is operating on this YLM theta phi. This is an eigenfunction of this. You will get h bar square L into L plus 1 into YLM theta phi. And well, LZ is acting on YLM theta phi. You get h bar m into YLM theta. Now, in some sense, this is like so. This is like YLM theta phi is like you have this abstract state L comma m, and then you take a coordinate basis representation of this, then you get this YLM theta. So this result that we have seen in the last class and this thing are same, except that here your L is only 0, 1, 2, 3, etc. Okay, so Here, L cannot be a half integer. Whereas here we have got both half integers as well as integers. So we have solved this problem in two different ways. Okay, so let's say we have angular momentum problem. So I could write, so I can solve this problem in coordinate basis. Then I will get eigenstates of L square and Lz as Lm theta phi. In this case, L is equal to 0, 1, 2, etc. And M is equal to minus L to plus L. This is same. And here you don't choose any basis. This is what we called as algebraic method. That means you start with commutation relations. Then you get these states L comma M. And here we find that L is equal to 0, half, 1, 3 by 2, etc. M is equal to minus L to plus L. Okay. Now the question is that why are we getting two different results? Here we don't have half integers, but here we have half integers. Okay. So we ask a question that why in algebraic method we get as integers and half integers. Okay. Now, so the issue is something like this. You started with the commutation relations, but these commutation relations are only commutation relation that we started with the commutation relation among Lx, Ly, Lz, right? But this L also has certain commutation relations with X and P. In algebraic method, we did not worry about that. So there should be some way those commutation relations will play a role, right? So note that L or Li or Lj, comma, so let's call it as xk. The commutator of Lj comma xk is also something like this: I epsilon j k m into xm. So this is how the commutation relation of position with the angular momentum will be there. Also, Lj comma pk is equal to I epsilon j k m pm. Okay, so I think I should write this h cross H cross, H cross. Very good. So this L also satisfies the same commutation relations. I would request you to prove this using the same procedure that we have used in the last class for angular momentum computation relations. Now you can ask a question that so these commutators must have a bearing in resolving the above anomaly, if I may call it as anomaly. So by using these commutation relations, we will be able to show that L equal to half, 3 by 2, etc. will not be present in this. But suppose if there is an angular momentum which has the same angular momentum commutation relations like L, but it does not share the same commutation relation with X and P, let us say. Okay. So in that case, that will have both integral and half integral values. Okay. So you can probably recognize what I am saying. For example, classically, if we have an orbital motion of a charge, okay, so any orbiting charge corresponds to a magnetic dipole, right? So orbital angular momentum leads to magnetic dipole. This is something in school physics we are familiar. Suppose if you, let's say you have a circle in which some charge E is moving this direction, and if classically we know that if there is a current I, okay, so let I be the current passing over a circular loop of radius R, let's say. So then you can say that the magnetic moment mu is equal to I times the area, that is equal to I times pi r. This is the magnitude, and the direction is perpendicular to the loop. Now, this I, which is charged by time, okay, suppose if this is moving with some velocity v, if this charge is moving with some velocity v, then this I is charge divided by time. How do I find the time? Time I will find out by So velocity time is basically the length, total length is 2 pi r. So this t can be found out by saying 2 pi r divided by v. So then I will get this as e v by 2 pi r into pi r square. So cancel pi, e by 2, and you cancel one r, v r. So I can multiply this m here and I can divide this by m. mvr is the angular momentum. So this is equal to e by 2m into L. Okay, this is a simple configuration. So in general, you can say that in general, we can say that the magnetic moment is a vector which is related to E by 2m into the angular momentum. So what is it that we are understanding here? We are understanding that the orbital angular momentum gives rise to magnetic moment. So that means any orbiting charge is like a tiny magnetic dipole, like a bar magnet. Okay, so that is the connection. So what does that mean? That means this will respond. Suppose if you apply magnetic field, this will respond as if it's a magnetic dipole. Okay, so that is what we have understood. But then people discovered that particles like these electrons, elementary particles, even if they don't have orbital angular momentum, they possess some magnetic moment. Okay, so elementary particles exhibit an intrinsic magnetic moment. Intrinsic magnetic moment that cannot be related to any motion. Okay, it cannot be related to any motion, but there is a magnetic moment. Okay, so that means what we have here is, so magnet, which I will call it as mu s. This is intrinsic to the particle. So when I say magnetic moment, I mean magnetic dipole moment. Okay, now I also mentioned here that it cannot be related to any motion. How do we know that this exists? Because these particles, so this can be known from from the way these particles respond to magnetic field. Okay. Now what we observe is that, so we have, like in the orbital case, okay, so we call this so now what we do is that in the previous case we have an angular momentum. That means there is an angular motion and there is an angular momentum associated with that. And in this calculation, we have said that that angular momentum gives rise to magnetic momentum. So what is the origin of this magnetic moment, mu? That is the angular momentum or angular motion. Here we have a magnetic dipole moment. But what is the origin of magnetic dipole moment? That question is not answerable. We don't know. That's intrinsic. That is why we are calling it as intrinsic magnetic moment. Like you say, there is a charge. Charge is an intrinsic property. You ask why charge is there? We cannot answer that question. Charge is an intrinsic quantity. Like that, this magnetic moment is also an intrinsic magnetic moment. Now one can ask a question, because there is a relation between angular momentum and dipole moment. Because here we have a magnetic dipole moment, can we define an angular momentum for this? The angular motion is not there. But for theoretical purposes, is it possible that we define moment? Hello?
Hello, sir. I think
So yeah. So my internet seems to be weak. I think I was disconnected again, right?
yes, sir. Yes, sir.
Okay, so let me see if I can. Okay, can you see it now?
Yes, sir.
Okay. So we could say that we can. So right word to say is that we can postulate an angular momentum. Yes. We don't know whether it is simply E by 2m, because here we are able to derive from classical electrodynamics, but here we don't know. So we will put some G and find out what G is from the experiment. So
Sir?
create a response to magnetic field. Yes.
Sir, this is okay. Mu s is G E by 2ms. But sir, there are some chargeless particles which also have a magnetic moment. So how that E by 2m factor will be there? In that case, how we can write?
Yeah. So so that is why. So what we are saying is, this is as far as electron is concerned, this is fine. But then we can also say that there is a neutron which does not have charge. Then also it has got this intrinsic magnetic moment. So this definition is not very general. Okay, so this is since the discovery happened mostly with the electrons, people tried like this. Okay, but it turns out that it is not even related to this equation. Okay, so what is the best thing to? What is the best way to say is that today news is
Sir, your voice is breaking, sir.
yes, like that you under the electron related to something else. But whenever is related to vectors. Now, what is vector?
Sir, your voice is not
So
clear.
what values can it take? Yeah. Hello.
Yes, sir.
Okay, so I think I have too small signal here.
Yes, sir.
George. Hello, George. I am not even knowing that I am getting disconnected.
Yes, sir. Sir, sometime skin gets stuck, sir.
Uh,
And now, but your voice is clear, sir.
yeah, but it is periodically going.
Yes.
What I am saying, we could write this as GF times yes. Effective need not be related to charge. Okay, but what is this yes?
Sir, we can't see your.
So what is yes? See the can you hear me?
Sir, voice is breaking, sir. And
No,
screen
sir.
got stuck.
Yeah. Are you hear me? Can you hear me now?
Yes, sir. Yes, sir. We can hear.
Okay. I think sharing the screen is taking more resource. I think it requires more. With the internet connection, I think if I share the screen, it is getting disconnected.
Yes, sir.
Okay, maybe what we can do is we can. I don't know what else to do because. So I don't know. George, is George there? Hello, George.
Hello.
George, I am not able to share and continuously present
Yeah.
because I think if I share, more bandwidth is required. So
Yeah.
can we stop for today?
Pardon?
Can we stop for today? Because
Yeah. If now maybe you can discuss some questions if they have, then we can
if you
conclude.
yeah. So maybe we will not continue with this, but if you have some questions, you can ask.
Good evening, sir.
Good evening.
Sir, generally in magnetic moment in school books, they mention a direction,
They mention.
direction or something minus.
See, magnetic dipole moment is a vector quantity, so it
Yes,
has
sir.
a direction.
Yes, sir.
Okay, so what is your question now?
So the direction of magnetic moment and the angular momentum is also same direction.
That depends on what kind of charge, So if the charge is negative, then they will
Okay.
be in opposite direction.
Okay, sir.
Hmm.
Okay, sir.
Yeah. Any?
Sir,
Yes.
sir, I joined bit late today. I came from office. I don't know whether you have published today. Sir, this for orbital angular momentum case, that eigenstate is that spherical harmonics, right?
Correct.
And the eigenvalues it admits is all integers and all integer values, right?
Correct.
So can we prove from the property of spherical harmonics that why it cannot have uh, half integer values? Is it possible? Once you ask this question, I think.
Yeah. So the point is that spherical harmonics will come as solutions of common eigenstates of L square and Lz when you try to solve the eigenvalue equation in the position basis
Yes, sir.
in the spherical polar coordinates.
Sir.
So that will admit only integer values.
Yes.
Okay. So from the properties of spherical harmonics, we will not be able to, from that we can say that half integer values are not allowed. The allowed values are only integer values.
Yeah. Yes, sir.
Whereas if you start from commutation relations, you can show that both integers and half integers are admitted. So we have to have some argument to say that half integer values are not allowed for orbital angular momentum. And the clue for that argument comes from the fact that orbital angular momentum also has commutation relations with position vector and momentum vector, because it is a classical, it has a classical analog.
Yes, sir.
So angular momentum components will have a commutation relation. No. So same commutation relations will be valid if you keep one as the angular momentum component and other as the component of whether position or where momentum. Okay, in fact, any vector operator. Okay, vector operator means what? An operator with 3 vector components. Any vector operator will have a commutation relation like angular momentum. Okay.
Yes, sir. Yes.
So these commutation relations have to be used in order to exclude the half integral values. Okay. It turns out that if you can use this x, y, px, py, these kind of operators, you can define some combinations of these operators, and then you can show that Lz can be written as a difference of 2 harmonic oscillator like Hamiltonians. That means if you look at the quantum numbers, it will have n minus n prime kind of a quantum number for Lz. That means your m in harmonic oscillator n is an integer. So n minus n prime will be an integer. So that means the eigenvalue of Lz will always be an integer. But if L can be half integer, m can also be half integer because m goes from minus L to plus L. If m cannot be a half integer, so should be L. So this is the argument which says that because of the fact that the orbital angular momentum has certain commutation relations with x and p, it should be this commutation relations that give rise to the fact that half integer values are not allowed for L. Now, when you come to this spin definition, since you are postulating this angular momentum will share only commutation relations with angular moment, like orbital angular momentum. This spin has no commutation relation with x or p or r or p. Because of that, this S can have integer values as well as half integer values. And since S can have integer values or half integer values, the total angular momentum, which is the sum of L plus S, can also have integer values as well as half integer values. Okay, that is this.
So, sir, when we do the angular momentum algebraic treatment, that is abstract, means it is valid for both spin and the orbital angular momentum, but the orbital angular momentum has a functional representation in position basis. That is why this restriction comes there.
Correct. Yeah.
Yes, sir. Sir?
Yeah.
Sir, that question also we could not hear. I asked, no, sir, how that means that magnetic moment due to spin is g times e by 2m times s vector. How that would have been for chargeless particle.
Yeah. So what I'm saying is that I mean, if you remember that initial efforts to understand Zeeman effect and normal Zeeman effect and anomalous Zeeman effect, people
Yes,
were always thinking in terms of the electrons, right? So electrons are they're in the orbits. So people were trying to see how these transitions are taking place when electron jumps from the Bohr-Sommerfeld model.
yes,
So
sir.
that time they were only trying to see this magnetic moment of the electron. So this E by 2m into G. This is because of the electron. But as you said, even if you have a neutral particle, there is spin. So in that case, what one does is they say that this magnetic moment is proportional to something called an angular momentum. So you don't write E by 2m, but you simply say magnetic moment is equal to some G effective into S, like that you write. Now this G effective may have relation to charge, or it may not have a relation to charge. That doesn't matter.
Yes, sir.
Okay, so but mu S is linked to some S. That much is true. But only thing is that proportionality constant may differ for different particles.
Yes, sir.
Sir,
Yes.
so regarding the previous question, I think that fundamental particles, we have the doubt regarding fundamental particles because neutron is not a fundamental particle. It is composed of quarks, and quarks are like have charges. We cannot see isolated quarks like free quarks, but they can have charge. They have charges. So if the
Yes.
charge and if we think from the perspective of electrodynamics, like for electric dipole moment, if we have a charge configuration whose total charge is zero,
Yes.
whose total charge is zero, then dipole moment will be independent of origin. So it will have a fixed dipole moment, electric dipole moment. So regarding that, we can have the analogous relation in magnetic dipole moment, because here we have like different charges, but like neutron is not fundamental particle. So like, and if they are not uniformly distributed and they are somehow like having some rotation within some rotation of quarks, which is
Yeah. So,
creating.
but what I'm saying is that okay, we don't have to really put so much effort to explain this, because if you say okay, neutron is not a fundamental particle, then what about neutrino?
Yes, sir. But what about photons? Photons, like
Photons, yes.
Yes, I
Yes.
also thinking like that. But like for fundamental particles, we have the doubt. But for like composite particles, we do not have, like, we can have some physical representation. But
Yeah.
question
See,
comes.
see, like for example, you take a composite nucleus. You write a nuclear spin, right? But nuclear spin is not it's not a spin of a nucleus is not a fundamental particle. It is made up of protons and neutrons,
Yes.
and you combine all those spins and write the spin of the nucleus. Like that, if you want to write down the spin of the neutron as a combination of spin of quarks, that is fine. But that doesn't simply answer that question that okay, if you have neutrino, for example, it has a spin, but that doesn't seem to have any relation to
Yes,
charge.
because neutrinos are structureless fundamental particles.
Correct.
But like, will neutrinos react like in some way if we put them in a magnetic field?
Yes. It has spin half particles, so it will react.
Like
It may have
photons
a
will
weak.
react in a magnetic field. Like we have like in the magneto-optic effect, but that is classical. No?
Yeah.
But like, I'm asking that photons or like somehow like this gravitons or like neutrinos, these possess like spins. So will they react in some way when I put them in magnetic field?
Yeah, I assume that see the spin of the photon is a different concept. I don't think it is related to the magnetic moment
Yes, but
or magnetic dipole moment.
Yes, but spin is related to magnetic dipole moment because the way we understand things, like it's the intrinsic dipole moment, magnetic dipole moment is like is equivalent to the concept of spin.
Yeah, that is true, but I don't know. I don't think with a photon that is the case. That is this whatever these spin one bosons are there. No,
Yes,
I think they are not related to magnetic moment. So that is one more abstraction of this one.
Yes.
Okay, but spin half particles, yes, they are related to this. Neutrino also probably it is related to this, but only thing is the strength of what is the
Interaction.
strength of interaction that will
But like
depend
neutrino
on.
doesn't interact in an electromagnetic way, I think. Neutrino is like neutrino interaction is very weak. Not
Yeah, that's true.
so like the spin algebra should be, this is not the ultimate picture because spin is something beyond this. Like this is this is something elementary.
Which one you are saying?
The spin commutation algebra, is it something elementary, like because spin of the photons or like gravitons, like or some other like neutrinos, we cannot consider them as magnetic moments.
Yeah, so essentially the spin, whatever spin that we are now proposing as a way to explain the magnetic moment is ad hoc only, because it is something which we are putting by hand. Okay,
Yes,
so what is observed is real. So what is the how it comes about is different for different things. No, like for example, if you take Dirac equation, for example, for spin half particles, the spin comes out of Dirac equation. That means it is a consequence of relativistic invariance and things like that. So in non-relativistic quantum mechanics, whatever we are doing is just putting it by hand.
yes.
Okay, so
Sir?
Yeah.
So, sir, this is the same G, no, that which gives quantum electrodynamics very precise value.
yeah.
Okay.
See,
Electro.
it is supposed to be. It is observed initially that it is 2,
Yes, sir.
but then quantum electrodynamics shows that it is 2 point something. It is slightly more than 2.
Yes, sir.
So it gives an accuracy of some 10 decimal places or 12 decimal places.
Sir.
Okay, so
We can think for like chargeless particle, this E by 2m, we can simply observe with that G and we say some constant time S vector. Like that we can think. For it.
yeah, that is what you do in nuclear physics when you try to talk about magnetic moment of neutron and things. Instead of Bohr magneton, you define something called nuclear magneton.
Yes, sir.
Yeah.
So we may not write, we cannot write it like E by 2m or factorize it.
Right.
Okay, then shall we
Okay,
close
yeah.
then?
Yeah, okay, we can close.
Thank you, sir. Good night.
Good night.